at problem 6 and 7. Yeah. So let's start with problem 6. So as you can see, we have the information about the separators. We have 2 separators and a stock tank. Yeah. We have the GOR gas oil ratio and the specific gravity of each separator and the stock tank, and also the reservoir pressure and the reservoir temperature, and also the specific gravity of the stock tank oil in API degree. So in part A, what we have to do is to find the average specific density of the produced gas. So yeah. So the information that we got in this question is a specific gravity of first separator, gas oil ratio of the first separator, and also the specific gravity of first separator, second separator, and the gas oil ratio of the second separator. Also the specific gravity of the stock tank gas, and the gas oil ratio of the stock tank. So in the first part, we need to find the average specific gravity of the produced gas or the surface gas. So which is the average of the first separator and the second separator and the stock tank specific gravity. Yeah, this equation. Specific gravity of the first separator multiplied by GOR of the first separator plus specific gravity of the second separator multiplied by GOR of the second separator. I actually don't have any space here, so continuing here, and the specific gravity of the stock tank multiplied by GOR of the stock tank divided by the total gas oil ratio. The total gas oil ratio, we know that is the sum of all gas oil ratio of the separators and the stock tank. So this is equal to the first separator GR and the second separator GOR plus the GOR of the stock tank. That is equal to standard cubic feet per STB. So now you can easily find the average specific gravity of the produced gas.
Hi, Puye.
Yeah.
The GOR of stock tank, isn't that not 25?
25. No, the information that I have here is 414.
So 25 in the file.
In the file, it's 25?
Yes.
Okay.
No, it was okay. It was 440.
So let me see the question. Oh, I just, yeah, I think I,
Yes, it was for separator.
25. It's 25.
Then the answer is correct. 5 to 9 is correct.
Is it correct?
Yeah.
Are you sure? Okay.
It's just the value written is wrong.
It's weird. So oh, yeah, it's the same, I think. Yeah. So the average specific gravity. Second separator. Plus the stock tank gas oil ratio 25 multiplied by specific gravity of the stock tank over a total GOR, which is 529. It's equal to 0.7262. Second part, we need to find the weight of the gas, mg. You know that m mass of the gas over the molecular weight of the gas is equal to number of gas moles. And also know that number of the gas moles is equal to total gas oil ratio over molecular weight. We can prove this by writing the GOR is volume of the gas over volume of the stock tank oil, and this is the molar volume. We assume that the volume of the stock tank oil is 1 stock tank barrel to make things easier. So this is 1, and this is becomes V gas at the surface is equal to number of the moles multiplied by R and temperature over the P. These are at the surface condition, and the molar volume is also R multiplied by temperature at the standard condition, and over the pressure at the standard condition. So simply it becomes, if we cross out, becomes the number of gas moles. So from this equation, can conclude that so the rate of the gas becomes molecular weight of the gas multiplied by gas oil ratio or the molar volume. So now that the molar volume is 380 and so the total GOR is 529. So we need to find the molecular weight of the gas, to find the weight of the gas. Now that the specific gravity of the gas is equal to molecular weight of the gas over molecular weight of the air is 29. From there, molecular weight of the gas becomes specific gravity multiplied by 29. Let's produce specific gravity. So it becomes 0.7262 multiplied by 29, which is equal to 21.03 pound per pound mole. So we use it here in the weight of the gas equation, 21.03. It becomes 29.32 pounds. So in the section 3, also we have to find the weight of the stock tank oil. You know that density of the stock tank is equal to mass of the stock tank oil over the volume of the stock tank. as before, we let volume of the stock tank is equal to 1 STB. So this equation becomes just rate of the stock tank work. This is one. So now we only need to find the density of the stock tank oil. The specific gravity of the stock tank oil is equal to density of the stock tank oil over density of the water. Density of the water is equal to 350.54 pound per barrel. So this stock tank density becomes density of the water multiplied by the specific gravity. And the specific gravity was so the density of the stock tank is equal to 311.98 pound per BBL. The stock tank density is equal to mass of the stock tank. Proved it, so weight of the stock tank becomes 300.98 pounds. So in part 4, we should calculate the pseudo liquid density of the dissolved gas at the standard condition. Let's do it. Pseudo liquid density of the dissolved gas at the standard condition. Now, the only ways to use the figures to find the pseudo liquid density of the dissolved gas. I think the figure is in the compendium 9. Yeah.
Oh, yeah.
Yeah.
Can I ask a question before you get into part 4?
Yeah.
On the calculation of the weight of the stock tank oil,
Yeah.
that formula that you have above, what is the difference between those two densities, the one on the left and right hand of the equation? They are both stock tank oil, but one is specific, did you say?
I don't get that.
So you have a formula right in the top of the sheet that you're showing, which is density of the stock tank oil
Yeah.
equals to density of the stock tank oil. They are both densities. I'm just wondering what the difference is.
You mean
It's in the third part.
part? So you mean
Just the one that you resolved. Just below, in the third part, yeah.
Yeah.
That formula that you have,
This-
no, the one below to the left.
here?
That one. Yes, that one. Is that density of stock tank oil
Yeah.
equals to density of the stock tank oil?
It's equal to weight of the stock tank oil.
Sorry, say again?
The weight of the stock tank oil. The mass.
No, yeah, but the one above,
Where?
the one that has the water, yeah,
Here? Yeah.
the one above, that one, the one that you're pointing just now.
Yeah.
Yeah, what are the, can you just call how the name of each factor, besides the water, of course, but the one above is density of stock tank oil.
Yeah. This is the specific gravity of the stock tank oil. So what do you want to know?
That's the specific gravity, and the one on the right, I mean, to the right side of the equation,
Is
is
the
that,
density of the stock tank oil.
so there are different.
Yeah, yeah, they are.
total.
Yeah.
One is the specific gravity and the other one is a density.
Yeah.
Okay.
So now let's get to the pseudo liquid density of the dissolved gas. In compendium number 9. This one. So as you can see, figure number 9.5, apparent liquid density of the natural gas. Actually, in the y-axis is apparent density of the dissolved gas, and in x-axis we have a gas gravity. So, and in the figure we also have the API of the stock tank oil. So the information that we need to use is just gas gravity and also the API degree of the stock tank oil to find the pseudo liquid density of the gas at the standard condition, you know, at the 60 Fahrenheit and the 14.7 psi. Just let me. The API of the API of the stock tank is 27.4, and the specific gravity that we calculated, the average specific gravity, is equal to 0.7262. just using these two information. 72, yeah, actually somewhere around here, I think, yeah. So let's just that.
Sir?
Yeah?
What gas gravity number are you using?
The average gas gravity that we calculated, 0.72.
You mean the specific weight?
Yeah, a specific gravity.
Okay.
Yeah. So the density of the pseudo liquid density of the gas at the standard condition is approximately 24 point something 9. At the standard condition. So let's go to the part 5, the pseudo liquid volume of the gas at standard conditioning. So simple. So the liquid density, volume of the dissolved gas. You know that the density is equal to weight over volume, because this is the pseudo liquid, so we assume that the gas is some kind of liquid here. So we use this assumption. The volume becomes weight of the gas over density of the gas that we obtained before. That is equal to density we found 24.9, density of the pseudo liquid density of the dissolved gas. And the weight of the gas that we found earlier, 29.32 pounds, and the volume becomes 1.17 standard cubic feet. In part 6, pseudo-liquid density of the reservoir fluid at the standard condition, not the reservoir condition, just standard condition. So to find the pseudo-liquid density of the reservoir fluid, there's a formula in compendium number 9, I think, yeah. Is weight of the stock tank oil plus weight of the gas over the volume of the stock tank oil plus the volume of the gas is equal to density, pseudo-liquid density of the reservoir fluid at the standard condition. We got all the information we need. You just need to make an assumption again. So let volume of the stock tank to 1 stock tank barrel, which is equal to converted to the cubic feet is equal to 5.6615, yeah, cubic feet. Now fill the equation. Volume of the stock tank oil is 5 cubic feet plus the volume of the gas here 1.17 standard cubic foot. Weight of the stock tank oil we obtained earlier, 311.98 pounds plus the weight of the gas, 29.32 pounds. So the liquid density of the reservoir fluid at the standard condition becomes 3.2467 pound per cubic feet.
Sir?
Yeah.
So this is the assumption that you've made. Let VSTO equals 1 stock tank barrel, and then it is 5.615.
Yeah.
Is that 7 or it's F, the other number?
This is the F.
This is F. It's not 7, right?
Yeah. It's feet. Yeah. Cubic feet. Yeah.
Yeah. Okay. Okay. Thank you.
So now that we found the liquid density of the reservoir fluid at the standard condition, in the part 7, you need to find at the reservoir condition. Yeah, density of the reservoir fluid at the reservoir condition. You just need to make some correction to the pressure and the temperature to convert the standard condition to reservoir condition. So chart that you need to convert the standard condition to reservoir condition and make some correction is in the this chart, and after figure 9.3 density correction for compressibility of the liquid or the pressure correction, and the chart after that the density correction for thermal expansion of the liquids, figure 9.4. So in these figures, you just need the density at the standard condition in x-axis, and also the pressure, which is the pressure at the reservoir condition. And then we find the correction that we need here in the y-axis. Also, this is true for the thermal correction. You just need to find the temperature of the reservoir and the density at the standard condition. Density of the reservoir fluid at the reservoir condition. We have the density at the standard condition. We found it above here. Just need to do some corrections. So the correction for the pressure is that density of the oil at the standard condition plus the value that we can find from the figure. And also the thermal correction. The density of the oil at the standard condition minus the value that we can find from the figure. reservoir pressure is 3,218 psi. And the reservoir temperature is 218 Fahrenheit. So using the figures that I showed you, the value for the pressure correction is equal to 0.9 at this reservoir pressure and temperature. And the value for the thermal correction is equal to 3.6. So adding to the standard condition to get the reservoir condition, density of the reservoir fluid at the reservoir condition is equal to standard density of the oil at the standard condition, which is 50.2467 plus, this is plus 0.9. That becomes 51 point pound per cubic feet. And also for the thermal correction, using this value, now minus the thermal correction that we found it here. It is equal to 47 point pound per cubic feet. So let's have a break for just 10 minutes and then we come back. So let's start again. And about problem number 6, I highly recommend you to practice it by yourself because it has showed up in a couple of final exams. So yeah, maybe this year too, who knows.
I was just wondering if, because you put up pre-recorded solutions for problem 3 and 4, I think I remember, or 4 or 5, will you be putting up a video of these problems as well for us to look back at?
Sorry, the final part of your question, could you please say it louder?
Yeah, will you be putting out sort of the same style pre-recorded solutions to these problems as well for us to look back at?
Which problems? Number?
The ones you're solving today, if we are trying to solve it after, later by ourselves and we get stuck.
I don't know, because I just uploaded number 4 and 5, and yeah, and number 1 and 3 we had the physical class 2 weeks ago, I think, yeah, and I solved this question there.
Yeah.
So, yeah, next week I think the problem number 8 and 10 will be recorded and published on Canvas, but number 6 and 7, because I just solve it here, I don't know, maybe in the future I can record it. Yeah.
Okay, that's all right. I was just wondering. That's okay though. Thank you.
Yeah, no problem. So let's go to the problem number 7. Separator oil and gas are recombined to give the 1 pound mole reservoir fluid, which means the number of the gas moles and the number of the oil moles are equal to 1, which is the 1 is the reservoir fluid. Number of the moles of the reservoir fluid. Yeah. So what we have to do is to.
Oh yeah.
Yeah.
Can I? Before again this exercise, I think the previous exercise, or I don't know if you mentioned it, but the previous exercise also had another part of calculating. What is it?
Part B.
Yeah, not only part B. Let me see.
Because the part
okay.
is not so important. Yeah.
Okay. No, it's okay. I can see that the solutions that we were provided had extra things that were not probably requested. I don't know.
Okay.
Okay.
So in part A of the problem 7, we have to prove this equation for the gas oil ratio of the separator. Our assumption is that we already know the gas oil ratio of separator is is standard cubic foot per separator barrel, and the separator oil density is pound per cubic feet, and also molecular weight of the oil separator. You just need to prove this equation. Assumption that we have is number of the gas moles plus number of the oil moles is equal to 1. We assume that this is reservoir and this is the separator. Number of oil moles, number of the gas moles. So in part A, we need to prove the expression, which is this one multiplied by number of gas moles multiplied by density of the separator oil by 5.65 over the number of the oil moles multiplied by the molecular weight of the oil. We prove this one. So, as we know, the gas oil ratio of the separator is equal to volume of the gas at standard condition and the volume of the oil of the separator. So first we need to find an expression for the volume of the gas at the standard condition and then find an expression for the volume of the oil at the separator. You know that the volume of the gas at the standard condition is equal to, using the equation of the state, number of the gas moles controlled by R and temperature at the standard condition over pressure at the standard condition. Because this is that the surface, the compressibility factor is equal to 1. So the volume of the gas at the standard condition becomes number of the gas moles multiplied by R factor multiplied by the standard condition temperature, which is 60 Fahrenheit, and then converted to Rankine degree over the standard condition pressure, which is 14.7 psi. This gives us the volume of the gas at the standard condition is number of the gas moles multiplied by, if we do some math work here, just dividing and multiplying, yet 579.5. This volume is in cubic feet. This is an expression for gas volume at the standard condition. So now we have to find the expression for oil volume at the separator. Know that the density of the oil is equal to mass per volume. Becomes mass or density. And also we know that number of the oil moles is equal to mass of oil over molecular weight of the oil, which gives us mass of oil becomes multiplied by number of moles. Using 1 and 2, volume of the oil at the separator becomes this one over the density. So dividing the volume of the gas at the standard condition, the volume of the oil at the separator condition, we can find it. You can see here the volume, the gas oil ratio of the separator. So this becomes moving the density to the numerator.
density of the separator oil is pound per cubic feet, and we need to convert it to pound per barrel. So use just the conversion factor of 5.6. So now we prove the part A expression. Part B, we have an expression for number of the gas moles and the number of the oil moles. Need to prove that again. So find the expression for number of the gas moles. Use the part A expression. And at the end here. So multiply the side of the equation by the denominator and dividing each side to the numerator. You can write we know that the number of the oil plus number of the gas moles is equal to 1. So number of the oil moles becomes 1 minus number of the gas moles. number of gas comes now multiplying each side of the equation to the denominator, we can get taking out the factor. First moving this one to here, so we can take out the factor. Take out the factor here. So now easily divide both sides of the equation to this expression to find the number of the gas mole. The expression is proved. So also need to show this expression for number of the oil moles. You have to prove it also. From point A, we found that the QR of the separator is equal to multiplying both sides to the denominator and then dividing by the numerator gives us number of oil moles Again, we know that number of gas moles plus number of the oil moles is equal to 1. So number of the gas moles is equal to 1 minus number of the oil moles. So this becomes this 2 plus this one. So number of the gas moles becomes 1 minus number of the oil moles. 1 by separated density. Doing the same things as before. Along the both sides each other. Again, moving this one to left side. taking out the factor. Dividing both sides of this expression. And this proved. Yeah. So for the last part, uh, says that check the composition of the will string based on the primary separator data. So we only need to find the mole fraction of the will string. I'll just give you some hints.
Sir, you will post the solutions, right?
The number of which one?
Sir, I mean the solutions. You will post it on Canvas, right? These ones, the ones that you're solving on the paper, I mean. Will you scan it and then?
Yeah.
Okay.
Yeah. Okay. I will upload it. Yeah.
Okay, but in which part it will be uploaded? In the exercise file?
I just have to figure out where can I upload and then I will let you know.
Okay, please put it in the announcement, okay?
Yeah.
Thank you.
So for part C, know that the number of the gas moles plus number of the oil moles is equal to 1. Find the mole fraction of the well stream or the reservoir composition, you just need to multiply this quotient to the mole fractions. So number of the gas moles multiplied by mole fraction plus number of the oil moles multiplied by the mole fractions of the composition plus the, so it gives the reservoir mole fractions. So to find this one, you just need to find the number of the gas mole, oil moles, and the number of the gas moles. You already have the composition, so we have the mole fractions of the oil and the gas. I can show you here the mole fractions from the figure 1. You have the composition of the separator gas NO and the separator liquid. The mole, we have mole fractions for gas and oil. Just need to find the number of the oil mole and the number of the gas mole. So using the expression that we proved earlier, number of the oil moles is equal to this one. And the number of the gas is equal to this one, on part B. To find the number of the oil moles and number of the gas moles, you have all these data except the density of the separator. You only need to find that. So then we have the number of the gas mole and the number of the oil moles. And by this formula, we can find the number of the reservoir. So the density of the stock tank oil, from the compendium number 9, is equal to sum of all mole fractions to the molecular weight of each composition over the sum of all so you have to find this one for each composition and also this one for each composition, and then sum and find the sum of all the composition, and then we can find the stock tank oil density. Actually, you can as you can see in the Excel sheet that is uploaded on Canvas in the exercise 5. So you can see that we calculate this expression density, the mole fraction multiplied by the molecular weight of each composition over the density of each composition for all of these compositions. And then the sum is 195.57. And also the sum of all the mole fraction multiplied by molecular weight is 155.0. So dividing this one over this one, and then convert it to the because the density is in grams per centimeter, cubic centimeter. So then convert it to the pound per cubic feet, gives us the 49 pound per cubic feet. This is the density. And also using the curve that I showed you earlier in question number 6, do some correction for pressure correction and also thermal correction, and add the pressure connection to this one, to the density as a standard condition, and also this one, do the correction. So the final density at the separator condition is 48.9. This is right. This is the separator condition, not the reservoir condition. So from the expression in the part A and B, now that we have the density of the stock tank, we can also find the number of the gas and the number of the oil. So, anybody have any questions?
Sorry, where did the can you repeat the part, the pink square, the C2, C1, C2, C7 plus, what is that? And
these are
the pink box, yeah. That.
These are, we have to find the mole fraction of each composition for reservoir condition, you know. Then comparing it to the data that we have in the question. This is the data we have in the
report.
Yeah, in the figure number 1 in the question. Yeah.
But how do we calculate the C1, C2, C7 plus? Where did they come from?
Yeah, I will
Thank you. Bye.
Goodbye, Puye.
Goodbye.
Bye. Thank you.
Bye.